In this video, we're going to talk about numerical integration. So these are actually techniques that computers use to be able to approximate values of integrals. And this happens for functions that we don't have closed forms that we can take antiderivatives of. And we've already seen this. So we've already talked about numerical integration in terms of approximations based on left-hand endpoints of rectangles and right-hand endpoints of rectangles. So this is a review of things that we've already done. Suppose we have this curve as our function, f of x, and we're looking at the integral over some interval starting at a and ending at b. That's the starting point and ending point. We're breaking it up into n integrals. Of course, in this picture, I've broken it up into 5, but you could imagine some generic number of n intervals, and those intervals, the smaller they get, generally the more accurate the numerical integration will be. The width of each individual integral is the total width that we're integrating over. That total distance is b minus a, the ending point minus the starting point, by the number of intervals that we have. So b minus a over n, again, that's a review from before. That's the width of each interval. And now I've added a couple of labels just to make our notation a little bit cleaner, that x sub I is the end point of an interval. So for this first interval, x sub 1 down here is the endpoint of the first rectangle. It's the right endpoint, because I started at 0. So then it means that x sub 1 will be the right endpoint of the first one, x sub 2 is the right endpoint of the second one, all the way up to x sub n here is equal to b, which is the end. Maybe I'll add this line here, because that's where we're ending our integration. And I'm going to add some new points too, because we're going to talk about, in addition to the right hand and left hand, we'll talk about a midpoint rule and a trapezoid rule. That's what we're building towards in this video. So before we get to that place, let's review what is the left-hand approximation, L sub n. I take this interval, I break it up into n sub-intervals, and we're approximating the area by rectangles. And again, this b minus a divided by n, that's the width of the base of the rectangle. And then f of x naught is the height of the rectangle, because I'm plugging in the point x naught, and f of x naught is its y value, which is a height. So in this case, the first rectangular approximation for L sub n is the area of this rectangle right here. And we're going to do that for every single one of where the left point is the height of the rectangle. And I could fill all of these in. Here, maybe I'll break these intervals up so that visually it'll be clear. Dot, dot, dot. And I can draw in each of these rectangles. It's going to get messy, but I used lots of different colors. So this is my Ln approximation. Recall that our Rn approximation is, wait, maybe I'll finish by drawing this last rectangle over here. Our Rn approximation is the same exact procedure. I'm breaking this up into rectangles, only instead of using the left-hand endpoint, I'm using the right-hand endpoint. So in this case, the width of each rectangle is given here, and the height of each rectangle is given here. So f of x1 is the height of the first rectangle in my right-hand approximation. The height is going up this way. And this visually, maybe it looks a little confusing. And in this case, for this rectangle, they appear, whereas this one, this rectangle would be down here. Again, this should all be review. We also want to talk about the midpoint approximation. So you can see that in each of these cases, like for this rectangle, the left-hand endpoint is way under, and the right-hand endpoint is way over, because the right hand would take this whole entire area, whereas the actual curve only covers, maybe 2/3 of that. So the midpoint rule gives us something that's a little bit more accurate. In this case, c sub I is the midpoint of the ith interval, so I can label that on this graph. So here's c sub 1, c sub 2, c sub 3, c sub 4, maybe I should call that dot dot dot, and this is c sub n. It's the midpoint on the nth interval, the last one. So how would I approximate this integral using a midpoint rule? I would have the base of each rectangle is the same base that we had before. It's the width of the base here. And then the height of each rectangle is the height of the function at the midpoint. So we can see that, at least for this first rectangle, you can think about this is actually a much closer approximation than the left or the right approximations. And f of c2 is going to be the height at the middle, and I multiply it by the width of the base, and so on and so forth. So this, my midpoint approximation, is rectangles base width of b minus a over n, which is what we had before, and heights given by the height of the function, maybe I should call this c sub I, curves. And for many curves, this is going to be a more accurate measurement. For linear functions in particular, it's going to be exactly equal to the exact value of the integral, because sort of this overestimation triangle and the underestimation triangle will be exactly equal for a linear function. We'll talk a little more about that in a second. There's one more type of numerical approximation that I want to talk about that's new, that some students conjectured actually when working on the first lab, and it's the trapezoid. Using rectangles to approximate these areas, I'm going to use trapezoids to approximate the areas. And let's recall, what is a trapezoid? So maybe even visually it's easier to see on here. My trapezoid rule, one endpoint and the other endpoint, and the area, instead of being the rectangle, it's going to be the area of this trapezoid. And for here, similarly, the next area is going to be the area trapezoid. So I'm connecting the endpoints with a straight line. And visually you can see that this approximation is actually going to be even more accurate than maybe our midpoint approximation. So how do we find the area of a trapezoid? The area of a trapezoid especially these right trapezoids are a little bit easier to visualize, that it's going to be the base of the trapezoid multiplied by the average of the heights. So if I think of this as height 1 and height 2, because there are two different heights here, that my area is equal to the base length of the trapezoid multiplied by the average of the heights. And what's the average of the heights? It's the sum of the heights divided by 2. So this is the base, and this is the average height. So what does that mean in terms of our approximations here? The base width is exactly the same width that we were dealing with before, b minus a divided by n, the total length divided by the number of intervals. And then, so this is the base, and now I need to multiply it by the average height. Well, what is the average height? The height of this side is the height that I get when I plug x1 into my function. So this is x0. I start at 0. So f of x0 plus f of x1 all divided by 2. So this is the area of the first trapezoid. This is the base. This is one height plus the other height, and they're averaged together. The next trapezoid is going to be really similar. It's going to be minus a over n times, what is the average height for this second trapezoid? Well, it's going to be f of x1 plus f of x2 divided by 2. F of x1 plus f of x2 divided by 2. And you can see that this pattern will hold all this last trapezoid, and the last trapezoid's area is going to be b minus a divided by n times the average of these two heights, which is f of x sub n minus 1 plus, can you see this? Yeah. f of x sub n all divided by 2. Whew. So really, if you wanted to compute it, this is the way that I would go about computing it. This is a really long way to write it out, and we can write it out a little more simply. Just like over here, we decided to factor out each of the widths of the bases of the rectangle, I can factor out each of the widths of the bases of these trapezoids. I can also factor out this 2, because I'm dividing each of these by 2, right? So then I end up with a formula, b minus a divided by n, but it's actually, because I'm dividing a half out of each of these, I'm going to change this into being divided by 2n, the average here. And then I have this long sum of things. And what is it that I need to add up in the interior? In the interior, I'm adding f of x naught plus f of x1 for the first one. And then I have to also add f of x1 plus f of x2 for the second one. And then I add f of x2 plus f of x3 for the third trapezoid, and so on. F of x sub n minus 1 plus. And notice what's going on here. Every time I'm doing these sums, the first endpoint is only used once. It's only used in this first trapezoid. But this right endpoint, or x sub 1, is used as the right height for this trapezoid, and it's also used as the left height for this trapezoid. So it's counted twice in here. And that's true for all of the heights along the interior, that this height right here is one of the heights for this trapezoid and one of the heights that's used for the average height for this trapezoid. And that's true for all of the interiors, which leads us with our final formula. And I'll write the final formula maybe on a separate sheet of paper to make it a little bit cleaner. I'll write it on here so that we have everything all in the same place. That t sub n is going to be b minus a divided by 2n. Remember, the 2 is coming from the fact that I'm averaging these heights. And it's going to be f of x naught plus 2 times f of x1 plus 2 times f of x2 plus 2 times f of x3 plus dot 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 plus 2 times f of x sub n minus 1. So visually I'm thinking of this one as the n minus 1. It's used twice on this trapezoid and this trapezoid. And then finally, the end 1 down here is only used once, plus just 1 times f of x sub n for our final ending value, which is b. So let's look at what this means. One thing that you might ask is, well, are these values going to be the same? Like visually looking at this, how clear is it that my trapezoid area is going to be different than my midpoint area? You can see that the shapes are different, but you might estimate that they would be similar to one another. And visually you can see that there's a slight difference, that if I'm thinking of the average height of these two endpoints, the average height of these two endpoints is going to be the midpoint of this line. So in this case, the area of this red trapezoid is equivalent to the area of this rectangle. And for this particular case, we see that the midpoint rule has a slightly greater integral value than the trapezoid rule, at least on this interval. On this interval, it would be the opposite. Or actually, all of them are going to be over approximations, and we'll analyze that here. So a question one might ask is, when is the trapezoid approximation or the midpoint approximation going to be an under or an over approximation of a function? And like I said before, if it's a linear function, these are going to be exactly identical to the actual value of the function, because, like you could see, if this were a straight line, the trapezoid would give you exactly a trapezoid, which is the exact area, and the midpoint rule would give you the average of the ends, which is exactly the midpoint for a linear function. So we're going to look at 4 different cases, depending upon the curvature of the function over the interval. And this is sort of a simplification because you could imagine that there could be some sort of critical point within the interval, but we're going to take our intervals to be narrow enough or small enough so that there aren't critical points within the interior of the interval, which with some calculus finagling that's possible to do. So first let's consider our midpoint rule. And I had a picture here and then I decided to erase it because I thought that it would be confusing. But how does the midpoint rule work again? So I'm going to find the center of the interval, and the height of my rectangle is going to be given by the height of the function at the midpoint of the interval. So this is approximated. You can visually sort of see that the over approximation, this sticking out piece, looks like it has slightly greater area than the under approximation portion, the part where the function is actually going above the rectangle. But we can be a little more rigorous than that. Here I'm going to redraw this picture down here. So if this is my midpoint extending up to the function, instead of writing this as a rectangle to approximate the area of this region, we can rewrite this to have the exact same area as the midpoint approximation, but I'm going to do it with, instead of having a flat top, I'm going to rewrite it to have a trapezoidal top. So bear with me for a second. What am I doing here? If you think to yourself, like the slope of this curve right here, if I wanted to, I could extend this to be sort of the same region. Like this. So what did I do? I decided that this rectangle has the same area even if I tilt the top, because tilting the top, the average of the two pieces, the average of the two end heights will yield a trapezoid that has the same exact area as if I started with the original rectangle. Does that make sense? So I'm pivoting and creating a new shape, this new trapezoid. It has the same average height and the same width. So this new trapezoid has the same area as the original rectangle, the original midpoint rectangle. Notice that this figure is slightly different than what the trapezoid rule yields. So for this particular shape, what did I do? I shifted the top of the rectangle into a trapezoid of equivalent area. And I did that because visually I can do that sort of easily here on this picture as well, that I think to myself, I'm going to maintain the midpoint as the same, and I'm going to draw a line that's tangent the top of this curve. And we see that it's going to be an over approximation because when I shift this into a trapezoid, the area is the same as my midpoint area, but I have this extra up here, and I also have this extra down here that I only have extra. So we found out that the midpoint approximation for an increasing concave down function is going to be an over approximation. Whereas, if I do the trapezoid, which I'll do in red over here, this is a little easier to see, that I take the two endpoints and we see that the trapezoid is going to be an under approximation because the trapezoid only covers this much, but the curve is covering a little bit more. And I'm going to use that same technique to analyze this one. So let's do the midpoint one first again, which is the harder of the two, that I'm going to find the midpoint of the interval, find the height of that, and now I'm going to try to draw a trapezoid that's tangent along this curve. So let's go ahead and turn, instead of using what would be a rectangle for our midpoint rule, I'm going to visualize it as a trapezoid that's tangent at that point. Shoom, shoom. So again, we see that this rectangle has the exact same area as this big trapezoid. Maybe I can color in the trapezoid. But this trapezoid isn't the trapezoid rule trapezoid, so not to be confused. It's really just a way to visualize this midpoint rectangle has the same area as this trapezoidal shape, and it has more area than what's under the curve. So it's also an over approximation. Whereas using just the trapezoid rule, again, the trapezoid is the average of the end points as the height. So in this case, t is going to be an under approximation. Finishing up, for these increasing concave up functions, you know it's concave up because it can hold water. It's sort of half of a parabola facing up. I'm going to pick my midpoint, and then I'm going to create a tangent line of my curve. And we see in this case that our midpoint is an under approximation because there's this extra piece on either side, whereas our trapezoid rule is going to be an over approximation because it's covering all of this extra area. And finally, for a decreasing function that's also concave down, our midpoint, picking the midpoint, it's going to be a rectangle. Our midpoint rule is a rectangle, but I'm going to draw the area of it with this trapezoid for visual estimation purposes, and we see that this is also an under approximation, whereas our trapezoid, which connects the two endpoints, is going to be an over approximation. And maybe I should draw in my midpoint rectangles so it's not confusing. It's not like we're doing two different trapezoid rules. This is just a way to visualize whether they're over or under approximations. Let's go ahead and do an example. So this is going to involve some computation, and so it's going to take a little while. And if you get bored, I give you permission to fast forward through it. But what we want to do is we're going to approximate the integral from 0 to 2 of e to the x dx using our M4 and our T4 techniques. So I've taken the interval and I've broken it up into 4 segments, and I'm going to label what are each of these segments. In my head I can even do it because I'm taking the total distance 2 and dividing it by 4. So in this case, b minus a over n is equal to 2 minus 0 divided by 4. And that means that the width of each of these segments is a half, so I can just count up by halves. And we need to do a little more work because for the midpoints of each of these intervals, they're going to be a quarter, which is a half of the half. And so I'm counting up by quarters each time. 1 1/4 is 5 quarters. And then how many quarters have I gotten? 1, 2, 3, 4, 5, 6, 7 quarters, which is just shy of 8 quarters, which is equal to 2. So let's approximate using M4 and T4, using our colors like we were before. Remember, M4 is going to be equal to the base of each of these rectangles. And in this case, we decided that the base, b minus a over n, is equal to 1/2, times the heights of each of these rectangles, and the height is determined by the midpoints. So the midpoint in this case, this is f of 1/4 plus f of 3/4 plus f of 5/4 plus f of 7/4. And it's always a good idea to double check that because we're doing 4 intervals, you want to make sure that you have 4 values added to one another. And I'm going to leave this actually as the exact value. In this case, it's going to be 1/2 of e to the 1/4 plus e to the 3/4 plus e to the 5/4 plus e to the 7/4. And I have my calculator right here. If I want to get a numerical approximation for this value, I can add 1/2 times e to the 1/4 plus e to the 3/4 plus e to the 5/4 plus e to the 7/4. I don't know why I did some of them as decimals and others not. I don't know. And it gives me an approximate value. Now, if I asked you for an exact value, this wouldn't qualify, but the approximate value is about 6.32299. I'm keeping a lot of decimal places in there. Let's do our trapezoid approximation. T4 is going to be equal to, again, the width of each of the trapezoids, which is 1/2 in this case. And then because I'm averaging each of these height values, maybe I didn't write my midpoint rectangles on here. I'll write those on here as well. Midpoint rectangles. That recall from our formula, this is going to be f of the starting point just one time plus 2 times f of the next point, which is 1/2, plus 2 times f of the next side. And I'm doing 2 of these because it's used in 2 of the different trapezoids, right? Times 1 plus 2 of f of 3/2 plus only 1 copy of f of 2. And notice I made an error, and this is a common error. So it's base times average of the heights. So I could average these heights, but remember that meant that instead of b minus a over n, it was b over a minus 2n. b minus a over 2n for our trapezoid width. So in that case, it's 2 minus 0 divided by 2 times n. We're doing 4 of them, so that's 2 times 4, which ends up being a 4th out front. So finishing this trapezoid rule, this will be 1/4 of f of 0 is 1, that's one I can do in my head, but 2 times f of a 1/2, that's 2 times e to the 1/2, plus 2 times e to the first, plus 2 times e to the 3/2, plus just 1 copy of e squared. And again, I can plug this into my calculator and get a numerical result. I have 1/4 times 1 plus 2 times e to the 1/2 plus 2 times e to the first plus 2 times e to the 3/2 plus 1 copy of e squared. And we see that our numerical approximation is about equal to 6.52161. I want to keep my decimal places consistent. Whoops, I should have written that in red. I guess it doesn't matter. Thankfully, we know calculus, and we can compare this to the actual result to see if it aligns with what we would expect. So our check, we can compute the integral from 0 to 2 of e to the x dx, because this is something we know how to integrate. That's the integral of e to the x evaluated from x equals 0 to 2, which is e squared minus e to the 0. and I can plug that into my calculator. E squared minus e to the 0 is 1, but I'll put it in my calculator just for fun. And this gives me a numerical approximation. So this is an inexact value of 6.38906. So notice, 1, that our midpoint approximation is closer than our trapezoid approximation. That this one is less than 1/10 away, and this one is 1/10½ away from the exact value. Another thing that we notice is that we can go back to what we saw previously. Looking at what we did before, for increasing concave up functions, you would expect the midpoint approximation to be under and the trapezoid approximation to be over. And that aligns, that our midpoint approximation was less than our actual value, and our trapezoid approximation was more than the actual value. The final thing that I want to talk about is error formulas. So we can be really exact about how close our error is. And of course, these are bounds on error, that our error could be less than that, or it could be more than that, depending upon the shape of the function. And we'll compute these for our specific example as well. These formulas are things that I don't expect you to memorize. These are something that I will provide to you on an exam. What I won't provide for you is the key of what each of the symbols within the formula means. So this is saying that our error bound for the trapezoid rule has something to do with the width of each of the intervals. That makes sense. As you get more and more intervals, they get smaller and smaller, and the error is going to decrease. And it's also dependent upon the second derivative. And that makes sense visually here, that, whether we got an under or over approximation had to do with whether the function was concave down or concave up, and the measure of concavity is our second derivative test. So K2 is a number such that the absolute value of the second derivative of your function is always less than K2 on this interval. So what exactly does that mean? I think it's easiest to see this with a specific example. So let's go back to our function that we were looking at before. Let's consider the error of our trapezoid rule when we were looking at the integral from 0 to 2 of e to the x dx. And in this case, I guess we did it for t4. So K2, the 2 comes from the fact that it's a second derivative. We want to find a bound for how much concavity we have within this interval from 0 to 2. And in this case, maybe it's our function f of x is equal to e to the x. And I think it's sort of a simplistic example because our derivatives are actually just exactly our functions, right? But it does make it. So we find out that on the interval from 0 to 2, the second derivative of our function is e to the x, which we knew because we took 2 derivatives of it. And we want to make sure that the absolute value of this function is less than a number. And we can look back and see, well, what is the maximum value of this second derivative on the interval from 0 to 2? And we see that if x equals 2, we get the biggest value. What value on here can I plug into here to get the biggest number out? If x equals 2, then the second derivative of our function is e squared, and that's as big as this number can get. So we're going to say that in this case, our maximum bound, our f double prime of x, is less than or equal to K2. I'm going to set that equal to the value e squared, because I know that any other value of x that I plug in, the second derivative will be less than e squared. So now we can go ahead and apply our error formula. So for T4, it's going to be, the error is going to be less than or equal to k2, which we've decided is e squared, times b minus a was 2 minus 0 cubed, all divided by 12 times n was the number of segments, and it's t4, so it's 12 times 4. So this is e squared times 2 to the third, which is 8, all divided by 12 times 4, oh, it's n squared, 4 squared. 12 times 16 is something I don't know in my head. I can bust out my calculator. 12 times 16 is 192. So that means that our error bound is approximately equal to 8 times e to the second divided by 192, which is 0.3079, about equal to that. So our trapezoid, notice that for these bounds it should be within 3/10. Ours was closer than that, right? That we were only off by maybe 1.5 tenths. Whoops, you can see the values. We were only off by 1.5 tenths with this trapezoid rule, but this error bound tells us that we have to be within 3. We can do the same thing, I've already started down here for the midpoint, and our values are the same. 2 is the same as it was before, it's e squared, the bound on my second derivative, and this ends up being e squared times 2 to the third is 8e squared, divided by 24 times n was 4 squared. So notice that this denominator is twice as big as this denominator. This was 12 times 16, whereas here we now have 24 times 16, which tells you that the error bound for the midpoint rule is always going to have less error than for the trapezoid rule. And here we see by numerical approximation we have 8 times e squared divided by 384. And we see that our error bound for our midpoint rule, so the error bound is telling me how far off is my midpoint rule from the exact integral. It's always going to be less than 1/10. And we see that back in our case that it was even less than 1/10, that it's only 5/100ths away. So that's a closer approximation than what we got with the trapezoid rule.